Hi, my name is James Higginbotham. Today we're going to talk about event-based API patterns and practices. We're going to start off talking briefly about event-driven architecture, map that over to async API styles that are available today, and walk through each of the styles to see the different kinds of options we have available. And then we're going to finish up talking about some common patterns that help us to design more robust and evolvable asynchronous APIs. First, a little bit about myself. I'm an API architect. I have a development background. I work with organizations all around the world to train their staff in effective API design. I also work with organizations to help them establish, grow, and mature their API programs. I'm based in Colorado Springs, but I travel all over the world, interacting with different organizations and worked with different vertical industries, including commercial insurance, healthcare, hospitality and hotel and travel, finance and banking, and even a startup airline that I helped get off the ground literally. API design is more than just technology. It can't just reside over in the corner and be forgotten except by a handful of developers. It really is the combination of business, product, and software engineering that makes them successful. Instead of just focusing on the technology aspects, we have to combine those concerns with the needs of the business, the type of business value they're bringing to the marketplace, and introduce product thinking and product design all together to make them successful. Therefore, it's an architectural concern. It's more than just a technology choice. Now, today we see a lot of popular API styles like REST, gRPC, and GraphQL used in synchronous fashion. We send a request to a server and we receive a response back. And there's nothing wrong with that. There's a lot of power in that we can use every day. But there is a lot more opportunity available to us if we start thinking about what it means to offer asynchronous or event and streaming based APIs in addition to those request response APIs. It really improves the number of interaction types that we can have and the kinds of integrations that we can offer our workforce, our partners, and our customers. In the async API world, we really need to answer different kinds of questions for the people that are going to be using our APIs. In the case of async APIs, we want to ask questions and make sure that we answer what happened, who did it happen to, and why did it occur. One example of this may be notification of a subscription or an unsubscribe event to a newsletter. So we want to know when those things occur so that we can take appropriate actions. Another example might be being notified whenever there's a new push to a Git repository so that we can trigger our build system. In this example, we have GitHub that's notifying us that a bot made some code changes so that it could upgrade some libraries that were known to have some kind of security vulnerability and needed to be bumped up to the next stable, secure version. So we get that notification, that triggers an event, and will then subsequently trigger our CI/CD pipeline to conduct a deployment. And those are just two examples. All of this eventing through these async APIs are built on some very core fundamental principles that we have inside of event-driven architecture, or EDA. You're at this conference because you're interested in these kinds of things. So I won't dwell too much on this. But if you're new to software development or new to EDA, let me just give you a quick overview of some things to consider. When we're building an event-driven architecture, we typically have message brokers in the middle. And those message brokers enable us to send messages between components through the broker itself without the components knowing about each other. So we have two different styles or two different interaction styles that we have available to us. One is point-to-point messaging. We usually define those via message queues. A message is sent from the component here on the left through the message broker, and one of the components will receive that message. The other one will not. If we then send a second message, message B, the message broker will dispatch that one, maybe using a round-robin technique to share that with the other component that didn't receive message A. But only one component's going to receive it. It becomes point-to-point, but the components are not aware of each other because the broker acts as middleware between them. Contrast that to the fan-out or pub-sub model, where whenever a publisher publishes a message, message A, all of the subscribers receive it at the same time, and they can act upon that message and perform different tasks in different ways. They, again, don't know of each other's existence. The broker is the only thing that they're aware of. But in this case, it broadcasts things out. That's why it's called a fan out or a pub sub. There's a third style starting to emerge. It's streaming, and it's been popularized by Apache Kafka. It uses distributed logs to append new messages to the end of that log, called a topic, and then our consumers can start from the very beginning and walk through each message, or just simply process the most recent message that's been added to the topic. This is a little bit different than pub sub, even though it looks very similar, in that each consumer can process each of the messages on its own. So it's very similar to a fan-out architecture oftentimes. However, there is a difference in that these distributed logs allow our consumers to walk back and replay messages that have been sent in the past. Whereas message brokers don't offer that unless we add that ability on top of it. So it's a much different kind of approach. Those are the three primary styles of event-driven architecture and the patterns that we use. Point-to-point, pub sub or fan-out, and streaming. So what does that have to do with async APIs? Well, if we have a basic understanding of these three interaction patterns for eventing, we can now understand and reason about these different async APIs and determine which one is going to be the best fit for us. So let's look at a few different styles. The first one, and one that's really popular and known by a lot of developers, is webhooks or webhooks and REST hooks. These are callbacks where the server initiates the call back to a subscriber, which may be another server either within the same data center or outside in some network accessible service like a public cloud environment. The webhooks make a post call to any subscribers that wish to be informed of the messages. So the server, the webhook server, dispatches the call to any of the subscribers via HTTP post. That means the server can initiate the call, and then the receiver, the subscriber, can take action on that, processing that message as they see fit or ignoring it if it's not interesting to them. Now, REST hooks, and you can find more about it at resthooks.org, was Zapier's approach to standardizing the APIs for managing the subscriber list. So it offers a series of APIs to manage the subscriptions for any particular topic that you want to offer webhooks for. It doesn't necessarily manage or tell you how to build the webhooks, although they give you some tips on how to do it securely and such. So there's some valuable information there. It is not a framework. It's not a library. It's a guidebook to implementing webhooks successfully and in a more approachable and standardized way. Now, one of the things we see commonly with webhooks is that the server wants to send something to the client. But in all asynchronous communications, all the components could be potentially servers and clients. And so we're seeing both unidirectional webhooks, things like the GitHub example, and we're now seeing bidirectional webhooks where systems are becoming aware of each other and they can send and receive webhooks. So not only can they dispatch to subscribers, but they can also receive webhooks and be subscribers themselves. So one of those ideas that we can see here is by looking at Cisco WebEx and Slack as two participants that are listening to each other's webhooks. Let's think about that a little bit. Let's imagine that we need to have some document review process or workflow implemented, and we want to do it with asynchronous APIs. Let's think about a messaging app here on the left with this person named Ash who says, "Can you please review this document that I've submitted?" When I submit that request, I dispatch to any subscriber a webhook callback to my subscribers to let them know that something is ready for review. This triggers an HTTP post call to some sort of URL that has already been predetermined that calls the webhook receiver, which receives that HTTP post and can then process it. One of the things they may do is send it to a workflow engine, which might be a communication platform like Slack, let's say. That message goes into the workflow engine with details about the message and hypermedia links on how to get to the article for review, details about the workflow ID that's being tracked, anything else. So Julie receives this request, reviews it, and determines that she should approve it. She then dispatches a second event through the workflow engine that contains the message that this has been approved. sends the message to the dispatcher, which then sends it via an HTTP post call to another webhook receiver that happens to be a different component within the same system that dispatched the original message, processes it, and updates things accordingly, maybe even posting a message into our Cisco WebEx platform to say that it was approved. So now both of them act as webhook dispatchers and receivers. So they're both publishers and subscribers. This is a more advanced use of webhooks that we're starting to see emerge as more and more systems support both publishing webhooks and subscribing to them in different ways. Another common pattern in async API events is server-sent events, or SSE. SSE allows a client to connect to a server using standard REST style interactions, typically a GET, specifying the content type that they want to accept. In this case, it would be text event stream, and then requesting that the server stream events back to the client as they become available. So unlike webhooks where the server initiates the callback, in this case, the client connects and then stays connected, waiting to receive events. These events typically have an event type, like seen here in this example, as well as data. And the data can be plain text, JSON, whatever you'd like it to be. So we can have different event types or event channels on the same request or the same connection, and we can stay connected to it until such time as maybe some of our middleware network, reverse proxies, gateways, things like that, get in the way and decide we need to terminate this connection. Maybe it hasn't seen any data stream back and forth in a while. In that case, the client can reestablish a connection, but can add, as you see in line 5 here in the upper left corner, last event ID. They can say, this is the last event I received from you, allowing it to recover from some sort of disconnect event. And then the server can start to stream events starting with that last event ID that you saw. So very powerful. It's client originating, not server originating like webhooks, but it gives us the ability to stream events and different kinds of events over the same connection over HTTP, and is a good option for those that have a REST-based API and the subscribers can't be guaranteed to establish an HTTP server like what is required with webhooks. So with webhooks, the subscriber has to be able to stand up an HTTP server, bind to a particular port, make that available to the webhook dispatcher. In this case, it's all up to the client. If the client can reach the server, they can communicate. Another option is Websockets. Websockets have been around for quite some time, are a little bit more popular than SSE, and they also support a bi-directional back and forth protocol. So the client initiates a connection to the server, requests that it upgrade to a WebSocket connection, specifies the subprotocol that it would like to use, whether it's plain text or some other kind of format. And then once they negotiate, they can send raw binary data buried inside that original HTTP request. So it allows all kinds of binary formats to occur back and forth, tunneled through that initial HTTP connection. Now you can see here that we have a plain text format, and then we have a SOAP upgrade where we allow ourselves to talk using the SOAP protocol as well. So we can do different kinds of things like that. There's actually a really nice reference that shows you all of the different subprotocols that are recommended and supported by IANA, and that will help you understand what kind of subprotocols are available to you. One other option that's starting to emerge is GraphQL Subscriptions. So we know that we can use GraphQL to issue data queries and shape our responses that come back. They give us a much more robust control over the response structures than we get by default REST. So we'd have to do a lot of work in our REST APIs to kind of get the equivalent. GraphQL, therefore, is used a lot of times for front-end APIs, for experience APIs, so that we can craft and shape the responses that we want. One of the additional options they give us are GraphQL subscriptions. We can define a subscription of what we want to listen for, perhaps limiting it by a particular criteria. In this case, we want to hear all new messages that are in room number 1, 2, 3. And we will start to receive data as those messages become available. So it allows us to use GraphQL to do request response, but then to add on client-initiated streaming back to the client from the server as new data becomes available. gRPC is gaining more popularity for a lot of microservices or service-to-service style communication. It supports streaming as well. What's interesting about gRPC, it is client initiated. It is not like Webhooks. The client has to make the call to the server first. But the client can stream data to the server. The server could strictly stream results back to the client, or it can be bi-directional. So we have options on how we define our streaming protocol and who's going to be streaming, or if both parties are going to be streaming. This is really powerful. It's denoted with a simple keyword in the IDL that defines the service, and all the underlying infrastructure is handled for you by the gRPC code generators that generate all the code from this description format. Then you just drop in your implementation on the server side, and the client and the server start streaming. Now, as we start to design the payloads of our APIs, it's important to keep some ideas in mind and apply some basic patterns so that our asynchronous APIs are more evolvable and robust. I love the quote here by Tim Bray. He says, if you're going to start emitting events from a piece of software, put just as much care into event design as you would do in specifying an API, because event formats are a contract too. Now, I couldn't agree more. Events are contracts as well, but we oftentimes relegate them to just whatever the code decides the event format should be, instead of treating them formally and going through review processes and applying patterns and practices like we would with a REST API, GraphQL, or gRPC. One of the methods and formats that we might want to use is the async API specification. And it allows us, very much like the open API specs allows us to capture any kind of REST-based API definition, or just like the IDL format for gRPC or schemas for GraphQL are used to define the data exchanged between them. Async API allows us to define the message exchanges between the components, and then to put protocol bindings in there so we can specify, is it hosted on Kafka? Is it using MQTT, AMQP, Websockets, Stomp, all these different binding protocols that are available to define. So we can define the message in a protocol agnostic way and then offer one or more bindings that you can use to subscribe or publish to those particular channels that are offered. Really, really powerful. There's also some nice code generators, documentation generators, and other tools as part of the ecosystem. So when we document our APIs, particularly our async APIs, we're going to have to go through some design effort. We're going to have to think about what things look like. And there's some common patterns that I've encountered over the years that I think are really valuable. The first one is thin event notification. In thin event notification, or thin events for short, we broadcast only the necessary details that indicate that an event occurred. It requires subscribers to fetch additional data to complete any kind of related tasks for it. So we would use this kind of event most often when we don't want to send data that could be considered stale as part of the event. We want to provide enough information to the subscriber for them to make a decision on if and how they want to act upon that event, but they're going to be required to make subsequent API calls to go fetch the latest representation of the resource that changed. The second design pattern is to take that first one and layer upon it hypermedia. So we can introduce hypermedia-driven events. One of the things about asynchronous APIs is they often couple really well with some sort of request-response API. But unless you know exactly where to go, it's not very obvious which API will give us the detailed representation of the resource at hand or that's changed. So in this case, we can use our thin events and layer on top of it hypermedia links that point to our APIs where we can go fetch more detail. So if we want to bridge our event notifications and our async APIs with our standard synchronous APIs with REST or GraphQL or gRPC, this is a great way to do it. Design pattern number 3 is event carried state transfer. You don't always necessarily want to have thin events. Sometimes we want to actually broadcast the event with the complete snapshot of the resource representation available at that time. That's when we use event carried state transfer. These events capture a snapshot of everything that's needed for the subscriber to act upon that event. It does mean that if the data is mutable, if it can be changed, then all of the associated data that was sent might be out of date. But in circumstances where you want to send a complete snapshot of the data at the time of the event, this is a great option. This is really common for things like message streaming, where we're capturing data state changes through the use of snapshots. And each time that we capture an event or a message with a data change, we capture the entire snapshot of all the data at once so that we have a historical representation of that resource at that point in time. Design pattern number 4, structured event payloads. One of the challenges with building event payloads is that we have a lot of information to convey. And it oftentimes starts off as something pretty simple, an ID, a name, a summary, and then we add a few more fields and add a few more fields, and pretty soon the event payload is very flat and very hard to deal with. So using structured event payloads allow us to group properties together that are like detailed. In this example here that you see, we have contact details and all of the fields related to that nested underneath it. We have billing address and all those fields, mailing address and all those fields, and you'll notice that the billing address and the mailing address share the same structure. Well, the client then may be able to leverage that by enabling them to build one struct or object and parse each of those top level elements, billing address and mailing address, into the same struct. So this allows us to drive evolvability of our asynchronous events and the structures of them, the designs of them. We can evolve the structure over time and reuse the same field names by nesting them under some top level structure. Now, the more structured they are, the more complex they are, and the more cognitive load we create for our API consumers that are trying to ingest these events and make sense of them and act upon them. But one level of structure like this is a really nice way to group fields together and to reuse structures on the client side. Pattern number 5, evolutionary event schema. So when we think about evolving our event schema over time, there's some things that we really need to keep in mind. One, we only want to add new payload properties that have default values or that are optional. That way we can ensure that our subscribers that receive these events are able to continue to process the payload that they receive for the event without having to encounter or handle specifically new properties that show up. Likewise, we don't want to delete existing properties because they're going to expect them to be there and then the code's not going to find them, and it may fail the processing of the event notification because now there's a field missing and it can't make the appropriate decision required. We also don't want to rename properties. Likewise, we need to be able to make sure that code is stable on the client side. So make sure the changes to your event payload structures when you design them take these things into account. That means we need to put a little thought up front into how we design our event structures so that when we move forward, we can put additive changes in, but we don't have to make any breaking changes, thereby causing our clients to break their code and have to upgrade their code as well. Design pattern number 6 is offline and error recovery support. While we always assume that our code is going to work all the time because it always works on our laptop, right? That's not always the case. We may have to deal with offline and error recovery support. This means that sometimes our subscribers may go offline and need to recover and play catch up. They need to see the events they haven't seen yet so they can process them. They need to be able to identify and troubleshoot these failures as well if there's some sort of coding problem. So it's important to have a way, either via an API or via UI, preferably both, to be able to see recent messages that were attempted for delivery, if they succeeded or not, and if they didn't, request redelivery of them in some way, or to be able to fetch a list of events since a particular timestamp or an event ID, much like what we saw with server sent events earlier. The last design pattern, separate internal and external events. There is a difference between internal events between your systems where we know more details about the components that make up your solution than the external events where we want to hide all of the internal details of how you implemented your solution and instead offer important information at the business level or at the system level. So there's a difference between an event that says a payment was processed and here's the order ID here at the bottom with all of the details that came back from a payment gateway, including the authorization server, the merchant ID, and all kinds of details that may either be too sensitive to leak or extraneous and unnecessary for the consumer and be confusing to the developer. So make sure that you're designing your APIs with the target audience in mind. If you're designing an internal event-driven architecture, you may have a lot more details for your internal events that are exchanged between components and between subsystems than with external events that are meant to go outside your immediate team or even outside the organization. So we've talked about async API styles. We've talked about the basics of event-driven API and how those fit into these async APIs. We've even talked about some different patterns and practices that we should be implementing when we design our event-driven APIs. Why does this all matter? Well, we're seeing, and what I'm seeing in a lot of organizations that I work with, is that we have an evolving enterprise platform at play. We used to have a lot of APIs that allowed us to connect our workforce together and connect our partners and our customers together. That's not going to change. What is changing is the jobs to be done and how we need to interact. So we have all these different messaging platforms that allow us to receive messages and even put workflows into them. That means that our applications that offer APIs or just our standalone APIs that expose particular digital capabilities of our organization are not enough. We need to start thinking now about where these interactions are at. It used to be that you went to a particular web application or mobile application to get things done. Now you can be in a communication platform and receive push notifications of things that need to be done, like determining whether you want to make an offer to a candidate that you just interviewed. The system that manages that workflow wants to reach out to you in your messaging platform and ask you to do something, not send you a link in an email to go to that application to get it done. It's shifting things, it's flipping things on their head. So now our events are really important to bridge these different systems together and create new and really interesting workflows. So in this case, we might have an API that can tell us and give us hypermedia links of what to do. Those hypermedia links are embedded inside an event. So the event says, would you like to make an offer? Or would you like to approve an offer to be sent to this particular candidate, yes or no? And here are the hypermedia links that you need to send a request to trigger the approve or decline, allowing the messaging platform to display a UI, give you some different buttons, and bridge the world of synchronous and asynchronous APIs together. Really, really powerful. Our enterprise platform is starting to evolve. It's going from just having some REST APIs on top of a data store to having these robust solutions at the top that are web, mobile web, native mobile, voice, IoT, edge devices, all laying on top of automation and integration and low-code builders and other types of solutions there that are built upon REST APIs, GraphQL APIs, gRPC, NetConf, RESTConf for our devices, all these different APIs. We're also seeing these web eventing and streaming APIs start to emerge that are empowering us to do new things. All of these are driven by our platform of digital capabilities made up of all these different API operations, queries, commands, and events that are produced underneath. And all of those are a result of the data management that occurs that our business analytics and machine learning produce back and forth to capture transactional data, infer new details and information from it, create new analysis, produces new data points, pushes those into new databases, which are then available for new queries, commands, and events. All of this combines together into a really robust modern enterprise platform. And asynchronous APIs and event-driven architecture are absolutely the backbone of how this is going to happen. So that's it for my presentation. Thank you for your time. If you'd like to reach out, drop me an email, connect with me on Twitter. And also, if you're really interested in APIs, whether they're synchronous or asynchronous, sign up for the API Developer Weekly. It's a weekly newsletter that I hand curate and share out some interesting articles each week for you to keep up with what's going on, find new projects, new articles, and new insights in the API world. Thanks for watching.